So next, we want to describe length contraction. So, we saw that if I do a Lorentz transformation in the x direction, then the new coordinates x prime and t prime are given by t times, say, cosh of psi plus x time sinh of psi, and this is given by t times sinh of psi plus x of cosh of psi. In fact, let me write this in a different form. Let me write this as, equation rather than matrix equations. Now, these relationship can be easily inverted because, what do we know? Is the Lorentz transformation is just a boost in some velocity v. So the inverse Lorentz transformation is just a boost with the velocity minus v. So when we go from v to minus v, what happens is that because v is related to psi by tan hyperbolic of psi, when we go to minus v, psi becomes minus psi. So these relationships are easily inverted, and they just become Tx is equal to the cosh remains cosh, so T prime of cosh of psi. Sinh become minus sinh, so we get x prime of sinh hyperbolic of psi, and this is T prime of minus T prime of sinh hyperbolic of psi plus x prime cosh of psi. So now, suppose that we have like a rod which is lying along the x-axis, and it's stationary in the reference frame S, and the the endpoint have coordinates, say, x1 and x2, and all the other coordinates like y and z are 0, and it's stationary. So now we make a Lorentz boost, and then we say, what is the length of the rod in the new reference frame? So, so what we do is that, we x1 endpoint is related to the new Lorentz frame coordinate, but we are measuring the length of this rod at the same time in the new reference frame. So the t coordinate needs to be the same. So this will be, say, t prime of sine hyperbolic of psi, and then we'll have x1 prime of cosh hyperbolic of psi. And similarly, we're going to have x2 will be related to, again, the t coordinate has to be the same in both cases, and then this will be x2 prime of cosh of psi. So the length of the rod is delta x, and that's given by x2 minus x1, and then thus we find that this is equal to cosh of psi delta x prime, where delta x prime is x2 prime minus x1. Or in other words, delta x is equal to cosh of psi delta x prime. For non-zero v, cosh of psi is greater than 1. We find that delta x is greater than delta x prime. And that's because cosh of psi is greater than 1. So thus we see that the length of the rod is the longest in the frame in which it is at rest. And if we boost to a frame where the rod is actually smaller, then we see that its length gets contracted. So this is called the Lorentz contraction or length contraction. So similarly, let's consider, say, a clock at rest. And suppose that the time between two consecutive ticks is delta t, and this is given by, say, t2 minus t1. Then if I do the, because the clock is, now if I look at the clock in a new reference frame, then what is the time period going to be? What is the interval going to be between two different ticks? So that'll be t2 prime minus t1 prime. And so that is going to give us t2 minus t1 cosh of psi. So that means this is equals to delta t times cosh of psi. And thus we see that, the interval between two ticks of the clock is larger than the intervals of between two ticks of the clock when it was at rest. So a moving clock, therefore, runs more slowly than a clock that is at rest. And this is known as time dilation. So one thing that I should mention in deriving the time dilation is that we are using this formula. We are using this formula here because in the rest frame where we started from, the two x's here are the same because the clock is stationary, and therefore the contribution from the x in this two in the delta t drop out, and therefore we just have the cosh of psi. So let's move on and talk about personal time. So this is known as, say, proper time. So suppose that we have some object that is moving in some arbitrary fashion, as seen from a inertial reference frame S. So the thing is that this object is not it's not performing a rectilinear motion. But what we can say is that, we can divide up this object's motion into small pieces where each of these small motions can be thought of as, a motion with constant velocity. So each of these little, segments of motion we can think of as happening in some inertial reference frame. So, so if we attached an inertial reference frame to the particle and take the time interval to be very small, then in that inertial frame, that particle is at rest. So the interval between these 2 points, ds squared, is, of course, in our S frame, it's, say, dt squared minus, say, d of x squared. But in the instantaneous rest frame, it's given by dt prime squared. Now, from here, if we take the square root of this equation, what we get is we get dt prime is equal to square root of dt squared minus dx squared. Now we can factor out dt. If I do this, inside the square root, I get the velocity of the particle squared. And so therefore, what we find is that if, the clock that is attached to the particle, started at t1 prime and it ended at t2 prime, then we can actually figure out what that time interval is by integrating this equation, where we integrate it from t1 to t2. Here on the right-hand side, the time is the time in the S reference frame. So dt, then 1 minus v squared, where v squared is, of course, a function of time. So this is known as the proper time.